Hello. Hi, my name is Ashrith, and I'm guessing this is the last session of the day, so I'm guessing everybody in the room is interested in actually being here. So I'm just checking. So I'm actually a security scientist at H2O. Briefly, just give you a simple introduction as to what we do. I'll take you through a tutorial as to what you can do using H2O. And one of the use cases that I'll be working with is a security use case, but it's a very basic use case, so it's not very complicated. If it is, please let me know. If you are actually interested in doing things, while I'm doing along, I can slow down and I can wait for you guys. That's not a problem at all. But I'll be showing you the step-by-step process so that you clearly know what to do and how to analyze data using H2O. Is that good? Any questions? You're welcome to ask me questions anytime through the session. You don't have to hold it till the end. It's not a big thing, so don't worry about it. Thanks. So I guess we have some more people coming in. Okay. So as I said, I work as a security scientist at H2O. Most of the times what I design is I design algorithms that detect anomalous behavior on networks and fraud using H2O as a platform. What exactly is today's talk? So just an introduction about H2O. We'll be talking about the architecture, the agenda that we'll be going through as to what we're presenting today. As I said, a simple definition of the problem. I'll also take you through how you can set up H2O. It's really simple, but if some people here haven't tried it even for the first time, then it'll definitely be helpful. Then through a simple process of data analysis and looking at the results. So a quick introduction about H2O. We are a company of about 80 people, founded in 2012. We're based out of Mountain View, and much of us are scientists and engineers. So you kind of get the idea of the composition of a company. The product itself is open source. H2O itself is a product for machine learning. It's got machine learning algorithms in it, so you can just start it off and run it. You don't have to code much. There are interfaces through H2O where you're not expected to code anything. It's just more like a click and use. But if you're experienced, I'm guessing because you guys are here at PyData, most of you would like to talk to any application through the Python interface. So I'm guessing you guys are like a lot more experienced and first-time user would be interested in using H2O. So the platform is distributed, parallel, and in memory, which makes it really fast and scalable. So this is a general view of our executive team. So Trevor Hasty, Trip Shirani, and Stephen Boyd are the three advisors of our company. Trip Shirani and Hasty have been statisticians at Stanford, and Stephen Boyd is actually professor of electrical engineering at Stanford as well. So they've been helpful in in designing our algorithms and platform. So as I said, what is H2O? It's basically a machine learning analytical platform. We've got linear models, we've got random forests, and we've got gradient boosted machines. We've also got PCAs for unsupervised approaches. We've also made it easy by having APIs for different languages. We have APIs for R. We have shouldn't I say that? We have APIs for Python and R, and of course we can talk to it through Java, Scala. You can actually talk to it through Excel and Tableau as well, which I will claim that I don't know how to do it. So if you have questions for that, please do email me. I will take it to the right person and I'll help you guys out with it. So I won't refuse that. We can handle big amounts of data, big data coming from from the disk or from HDFS, or if you have a lot of it stored in some kind of a memory. So it's easy for us to handle. So of course, the machine learning space is divided into two parts: the supervised and the unsupervised. In the supervised space, we support GLMs, naive Bayes, which are your statistical, your classic statistical approaches. We have ensembles, which is the random forest and the GBMs. We also have deep learning. I believe Fabrizio should be in the audience here. Hey, so he will be showcasing a really cool deep water presentation on Sunday. You guys should not miss it because it's path-breaking, development in deep learning and deep learning's approach at H2O. So you guys should not miss that. In the unsupervised space, we have k-means clustering, PCA, and autoencoders, which we use on a daily basis for our analysis. So what's the workflow? How does H2O actually work? So H2O itself is a simple JVM, which you can run on your system itself, or you can run it through Hadoop and Spark. And you can get the data in through HDFS, native disk formats, and S3, SQL, and NoSQL. You can use Spark and Hadoop to run H2O. Things run in parallel, in memory, as I told you earlier. And you can interact from the multiple sets of languages and applications through H2O together. H2O also has its own native in interactive format, which is called Flow. It's actually a web interface, which is kind of really easy if you're starting off. It's a simple point-and-click interface that helps you quickly learn how H2O works, how to play around with it. And as you progress, you can talk through the REST API to it with H2O. So as we are here at PyData, in a very simple way, this is how you actually pull in data into H2O. It's as simple as just H2O import file, and you can get in your file in. So this is a general architecture of H2O works. We have the H2O cluster where you have multiple servers, built as a cluster. Then you have a source of the data. So using Python as a language, we talk to this cluster using the REST API. So using the REST API, the data gets called into the cluster. Now the data gets read in parallel into the cluster, and it actually exists as a distributed data frame in the cluster. And in Python, so you can actually see the data frame as a pandas data object. It's very similar to a pandas data object. I don't want to say it's the actual thing. It's very similar to it. But in essence, it's actually a pointer to the data frame that exists on the cluster. So if you were to disconnect yourself from the cluster and try and see what this object is, there would be nothing out there. It'd just be an empty pointer. The same thing in R as well. We have primarily focused on getting the data to be on the cluster, just so that the code is optimized to run faster instead of moving things from your local machine to the cluster. So in this diagram, it's basically the same thing, but what we would like to highlight is that you can access the data from your HDFS as well. You can read in the data from HDFS, and because HDFS itself is served on multiple clusters, you can have your data read in parallel, which makes it even more faster into the H2O cluster. So today's agenda, we kind of had a fair idea of what the architecture is. We'll use the H2O Python API to work with the problem and a simple data analysis. We'll also look at what kind of a model we did, and we'll look at how we can interpret the results. So the problem that we'll be working today is one of my most favorite problems that I've worked on for probably about 9 years now. It's basically trying to analyze and correlate security events across an enterprise organization. So I'll just give you a quick example of what happens. So you have network devices, you have system devices, and you have endpoints. Now all these devices actually are creating logs, and they're sending out information to one central logging machine. Now all these logs tend to get accumulated or aggregated at that point. Now if you're a security analyst, you want to be able to identify what event is happening in sequence to what event that already happened. So you want to be able to correlate, create a time series analysis of these events, so that you want to find out if something bad happened. If somebody got attacked, or if a sequence of events happened that led to an attack, you want to be able to immediately identify it. And that is something that actually people here at Capital One have implemented. So here I'll be showing you a very simple version of it. It's not at all complicated. It's very simple. What we're going to try and do is, so basically all these logs get aggregated, but before you get to a point where you can analyze these correlational events, you want to find out where these logs are coming from. Because practically what happens is, when you have hundreds of different sources of logs, you don't know where these logs are coming from. There are multiple machines of the same kind, sending the same kind of logs, so it becomes a problem. So in today's problem, what we'll do is we will identify the logs, we'll identify the sources of the logs, and using machine learning, we will try and predict the source of the logs based on what information we get in those logs. So that's the basic premise of what we're going to do today. Any questions up till now before we go ahead? Anything at all? Any questions about H2O, what we're going to do? Yeah.
I may have missed this. Is this supposed to be a hands-on tutorial? Or?
It is a hands-on, yeah. I was just,
Okay.
Yeah. So, yes?
Sort of a question about the problem. So we're assuming that it's not going to be robust if we try to do some kind of synchronization or orchestration beforehand. We're just doing machine learning because it's going to be too hard to agree on tokens.
So you're actually doing machine learning primarily because there are lots of log sources that you do not know where they're coming from. So you're like, okay, let's go probabilistic. We don't need to be deterministic in this, because much of the logs have very similar behavior. So you're going very probabilistic because there's a very good chance of being accurate. Okay, so what I'll show you is, can you guys see the data, or is that a bit difficult for anyone? The people in the back? Okay, thanks. Oh, Adam's. Hey, Adam. So what we have here is the sample data. This is actually a sample of the logs itself. Here we have logs from three different machines that have come in. We have, from the DHCP, which is basically your domain servers, and you have your VMware servers. So 3 different kinds of servers. So now you want to be able to classify them in their own, bins. So we start looking at this data, and what we find is they all have something really interesting, at the top right corner. If you see on the left-hand corner of all these logs, they have a number enclosed in, in a greater than and lesser than sign. That seems to be very peculiar. The next thing is, you see that the dates actually are kind of interesting as well. The dates are not the same all across. So the dates could be used as one way of identifying what these logs are. And you also have the process. In the first log line, you have DHCPD. In the second log line, you have VPXA, which I have actually highlighted. Again, I'm hoping that the people in the back can see it clearly. Okay. And you also have things like, you have IP addresses and you have MAC addresses in these as well. So if you go ahead a bit, these are a fair good set of features that we can think of. So you can look at these IP addresses, these different types of date formats, where the number that you saw in the left-hand side, which is actually called the priority level. The priority level is an identifier that the system tells you that at what priority you're supposed to read this log. Is it really important? Is it, is the house burning down, or is everything okay? So it's that kind of an indicator, and that's very important when you're reading logs. One thing that we also see is these logs tend to have a certain length, number of characters. Logs coming from the same sources kind of look similar, at least in terms of the number of characters it has. And if you observe a bit more carefully, maybe not in this case, but if you look at a large number of logs, you would probably see that the words that are there in certain logs that are common are actually the same thing. So you have similar kinds of words in logs that come from the same source. So using that, let's go ahead and think of these as a first set of features. So as I said, the priority value, which is the number on the left-hand side, the date format. The date format, we'll actually classify it as 5 different date formats here. What you can see in the sample log is actually 2 different kinds, but what we have identified in the data itself is 5 different. So we'll keep that there. And the number of characters is going to be another feature. Number of IP addresses is another one. Number of MAC addresses. And finally, we'll also look at what is the fraction of the words that exist in the log, okay, of different sizes of characters. If you have a word of 4 letters, okay, out of how many different words does this? I mean, how many words actually make up 4 character words? Is something that we look at. So let me take you to. Let's see. Okay, so before this. Is everyone here ready with H2O or the package? I would love to go over that with you guys if someone wants to try it out. Anybody here interested in trying it out? How to get it to start? Okay, so we have people. Okay, so let me take you down there then. So let me put that link up. Let's see. So the link you'll actually have to go to is h2o.ai/download. And you'd see on your left-hand side, you'll see H2O. You can just click on that. Let's see. So you can download the latest table so that you don't want any surprises. And you'll get to another page where you'll get a zip file. If I'm going fast, please just raise your hand and stop me. That's perfectly okay. Or if I'm going too slow, raise your hand and say that as well. So.
I don't think we'll be able to download it today. It's 175 megabytes. So
Oh, is that
it's going to take a while to download.
is that going to take a while for you guys?
It's going to take. It's saying it's going to take 1 hour to
Whoa.
download.
Oh. Okay. You should have got ahead of the line then. So. Okay, maybe anybody's got spare USB keys in case we can probably do that, but maybe not share it. I think that would be a sad thing. Okay. So let's assume you've got the downloads. And so next, what you need to do is you need to install the Python API, the Python package that you need for H2O. If someone's actually in the process of downloading and would want me to slow down, please let me know, like right now. Okay, cool.
Delays.
Okay.
Amazon's slow.
Oh.
As usual.
Do you know what's the estimate that you've got?
It keeps timing out.
Oh. Okay. You got 5 minutes? Okay. Okay, keep going. Okay.
From my standpoint,
Are you a Python 2 or a Python 3 dependency?
Python 2. Okay.
only.
Right now, yeah. Because that's what I'm set up for. Otherwise, I could have done the. So now, if you want to install, the Python package as well. So, can you? Hang on. So, you can do the pip install request, tabulate, and scikit-learn. Now, you can also install, saying pip install H2O. You don't necessarily have to go to this link, but if you can get to that link and use that specific package, it would be great. Is it? Oh, okay. Sorry, I didn't check that myself.
No, that's just if people are rolling down
Okay.
zip, they can unzip it, and the wheel file's already in there. So
Oh, is it? Okay, thank you. Yeah. So the wheel file is in the zip itself, so it should be ready.
Can you use it on 3.5?
3
Use it on 3.5?
H2O version.
Might not.
Oh,
It says 2.7.
yeah. So right now it's 2.7 is what we're supporting. Yeah.
Switch over to 2.7.
Yes. Myself. Apologies for that. Anybody successfully downloaded it?
Question for you.
Yeah.
Just install the pip version, pip install H2O. Would that be adequate?
No, that would just give you the Python package. It
Right, but I mean, would that replace your last line there on the page?
Yes. Yeah.
Okay.
Python package you're timing out for some reason.
Oh.
We timed out essentially when you're trying to download the package.
Okay.
I found that last time it was the same issue.
Okay. Are you on? Can you like get off to another network or something which supports it? I'm guessing it might be the load to Amazon from here, is what I would believe. So I think we probably should have hosted it locally. It might have been easier. Anyone still trying to download, trying to install Python package or the JVM? Or the jar? Oh, it took a long time? Okay. Okay. Cool. So now let's assume that this thing is there on your computer, which unfortunately it's not the case, but and after you've got the H2O package, all you have to do is just unzip it, and this is what comes up. So you have your Python package. I think you had mentioned that it actually comes with it, so that's a good thing. And you have the H2O jar and the R library as well, and the packages. So to run this, all you got to do is you have to run it this way. Let me just show you. Sorry? Okay, let's try that. Can you see it now? Okay, cool. I think I might have a session running. Let me just check. Let me try this again. So if you can see, you literally have to run just java-jar and h2o.jar to get the package up and running. And that starts running the server. So now you can I tend to forget my IP address, so I'm just copying that. Okay. So, and then you'd have to get onto your IPython notebook, or I think Jupyter Notebook is what it's called now. So Just run that, and if you have a session running on your Jupyter notebook, that'll be great. Anyone have any trouble with their notebooks? Anyone? Yeah. Oh, okay. So you
Is it on GitHub or?
you can actually download. Hang on, let's pull that up. Google is there for everything.
What he means is a pre-made notebook. The
No,
one
no,
that's
the
visible.
file itself.
Oh, the one I've made itself. Okay, I can share that to you after the session if that's okay. Is that fine? Okay, cool. So, I mean, I don't mind going slower for you to actually type things out if that's something that you're interested in. Okay, so, you call in the the H2O library. Let's hope it runs. Yeah, that's good. So from the H2O library, we also call the GBM estimator because that is what we'll be using to classify our logs today. And the way you connect to the server is h2o.init, where you provide the IP address, the port number, and it's always good to use strict version check equals false, primarily because we tend to do releases every 2 weeks. And if you are an enterprise and you tend to move a lot more slow than 2 weeks, which I'm sure you do, you don't want to be committing yourself to the latest version. And this thing will fail every time. So if you set this to false, it'll work fine, but you won't have some features. But if there's a big feature, we'll actually let you know, and you will be expected to move to the next version. So just remember, you got to do that, just so that it's easy for you for your daily working. And once you connect, you actually get some basic cluster information, as to what's the amount of memory, how long your system's been up, who's logging in, and stuff like that. Now, it's exactly the same way when you connect to a remote cluster as well. There is no difference in how you connect to a remote cluster. It's basically the same thing. Right? In this case, what I'm doing is I'm running the server on my local machine, and I'm connecting to that. And it's working fine. It's the same way when you connect to a remote server. Now there are situations where you have LDAP access, or you need to provide passwords to get onto those clusters. At that time, there are actually parameters you can provide in this call itself, which will help you access things through LDAP or using a password and a username. So you can do that as well.
You can connect to any node in the cluster.
No, I believe there'll be like one kind of a main node, master node, that you need to connect to. So I kind of jumped a step. Let me just take you back to my slides. So after we've got these features. Now, so you can just take some time. If someone is still setting it up, please just use this time to set it up. I'll just run through some basics of what the data, parts of the data. So after we've got these features, now the next thing that we need to do is we need to be, labeling the data, because right now we don't know what these logs are, where these logs are from. Now, primarily because this is a supervised learning approach as well. So what I did is I went ahead and actually labeled the data. Because I knew what each of these log sources are from. So the way we label it is something like this. So if you look at it, on the left-hand side is a text token that is unique to a certain kind of a log. And on the right-hand side is actually a label. So if you see the first token, which says rsa.ims.authn, is actually from the RSA secure ID systems. Okay, and ASA is very clearly from Cisco ASA devices, and something which is ACC with 2 brackets is actually from the big IP network, and so on. So basically, what we did is we took unique specific tokens from logs, and we actually identified them as to what their source is, and we labeled this data. Now, the reason, I'm repeating this again, the reason we did this is because this is a supervised approach, and we need these labels to be there so that the algorithm can actually learn what kind of log comes from what kind of source. And that is why we went ahead and we did this. Yeah.
So on the left-hand side, those strings are they contain wildcard characters?
We avoid as much as possible to not have wildcard. We want it to be unique enough, but not have wildcards in them.
You have person, backslash, and all that stuff. Is that absolute data? Or
Yeah. So so if you see the percent is actually escaped, so that means it's actually it's taken as is. Yeah.
I'm going to go into this in like 5 seconds, but I just wanted to ask you, why are they .text? Are you gonna?
Oh, good question. Yeah, so I didn't change that. I should have changed it. But initially, we were having so many different logs. We actually had to create separate text files for each of them. And the code, the initial set of code that I wrote for this was processing this data separately, and piping them separately and putting it into a separate text file. So, which is why it remained the same way. But yeah, good catch. Nice. So after we've labeled the data and we've identified these features, then we basically get the data in shape so that we can push it through the model. And this is how it looks like. So what you see here is the data that we'll be sending into the H2O algorithm. So let me try and explain the first one for you. The 30 is actually the priority value that comes from the data. The 5 is the date format that existed in that specific log. 138, by the way, before I go ahead, can you guys see from the back the numbers and everything? Is that okay? Okay. The 138 is, sorry, yeah.
sorry, on the previous slide where you have defined the data, is this a complete set of data or just a sample?
This is a sample. Yes, this is a sample. The total number of log files that I was working with is about close to about 135. So
Maybe I don't ask the question right. So the left-hand side is a pattern or is it absolute data?
no, it's actually a pattern in the log. So across a log, which is like so many characters long, that is a unique token to identify that this is a security log. And by the way, just for information, this is how current day security analysts identify logs. They don't have an algorithm which uses machine learning to do it. So if you're using Splunk in your enterprise environment, they actually use these kind of tokens. They have people who write these tokens on a daily basis and who update this onto Splunk servers across the world to catch these logs. So that's what they do. So the data gets formatted into this format, which is, so 30 is basically the priority value, 5 is the date format, 138 is the number of characters, 2 is the number of IP addresses in that log, 0 is the number of MAC addresses in the log. Network ID is the actual label, which is the response in this case, and following which you have words that are from 4 characters long to 15 characters long. So basically what it's telling is the fraction. So in the first case, you see 0.4, 0.2, 0.2, and then a 0 and then a 0.2. It's basically telling you that there are 4 characters, that 40% of the words in this log are actually 4 characters long. And 20% are 5 and 6 and 8 characters long. There is nothing which is 7 characters long. So it's basically measuring the number of characters in each of these words. And all the words that we actually measure must be available in a dictionary. So we don't take random, character strings, which are 4 characters long or 5 characters long. They must actually exist in a dictionary. That's what we try. It's the same thing with the next log line as well. You see the priority value is 166 and so on. So any questions up till here? Yes.
They must exist like as an English word?
Yes. Yeah. Sorry, they must exist as an English word, yeah. Okay. So, so now that we've got, we've formatted the data that's ready to go through the H2O algorithm, what we do now is we take that data. So what you see down is we are entering the path where the data exists, and let's run it. And so that has been processed. Now we import that data into H2O. Okay, that was quite quick. The next step that we also do is we define what these columns are. Now, this is important, because when you're analyzing so many different fields, which people normally tend to do in a machine learning platform, using a machine learning platform, it's good to know, what you're analyzing. So H2O.init. There is also H2O.connect, but if you're using a cluster. Oh yeah, okay, let me show you that. So it's Java space -jar H2O.jar. Let me just. Yeah. So okay, good thing that we are actually here. So here you can use this when you're running the Java or the H2O jar file. You can actually use the output of this as a debugging process. So let's say something goes wrong through your REST API call, or when you're using Scala or Java or something. Everything gets actually logged in this interface. So you can scroll through this and see if there is any trouble. You can figure out how things are working. If things have failed, if things are crashing, this will actually tell you. So this is a really good place. This is a rich source of data for you to keep an eye on when you're using H2O. So coming back, here we'll actually define all the columns that we have and just get a fair idea of what the columns are again. So the next thing what we do is in the process of machine learning, you actually have to divide the data into training and testing, or training and validation. Now the training part is where the machine learns, or the algorithm in this case learns what the data looks like, or what the data is in terms of its inputs and its response. So it's if you were to be looking at linear algebra, you give it a bunch of problems which is x plus y equals 10, or 2x plus 2y equals, let's say, 40. So that's how it's supposed to learn. Sorry, 20, not 40. And that's how it's. So when you're given these kind of algorithms, that's how it learns what those values could be, and that's the part of the training that actually happens. So here, what we're doing is we're taking 80% of our data, and so we're taking our entire data set and dividing it into 80 and 20%. The 80% actually goes as a part of training. And then we use the knowledge that we have learned from the 80% to predict on the remaining 20%. The next thing that we have to do is, after we've defined what part of our data actually becomes a prediction and what part of data is the training, we also have to define what are the input variables and what is the response variables. And that is what you define here. So if you look at it, what we define in our Y is basically the log class. What class does this log belong to? And the rest of the data actually goes in as inputs. And as I said earlier, we are using GBM, H2O GBM model to classify this. And this is a multi-class problem that we are having. Yeah, go ahead, Fabricio. Is the notebook? No, it's actually not posted yet. Much easier. Okay. Yeah, I think I missed that. Yeah, my bad. Sorry. Do you have a location where you can post it? I can give you the. Just a second.
I think it would be useful. I don't know. I was trying to type it to answer this one. It was a bit hard.
We don't have the data, so even if you have the notebook, it doesn't.
Yeah, I'll have to send them the data.
Oh, you don't have the data.
Yeah, I'll have to clean up the data. And send
Oh,
it. So it's okay, yeah.
I tried.
So here we're actually defining the model that we're using. We're using the GBM here, and you can define the model. And one of the things that you can also have is you can score each iteration. You might want to see how each iteration scores, and you want to see the result of each iteration. In our case, we're actually setting it to false because it kind of takes a lot of time, so which is why we're not doing it. But you could do it, and it'll give you results, and you can find out how good each iteration, how your iterations are progressing. What we'll do is we'll just look at the final results of each of these iterations. We also define the number of trees, how many trees are going to be used for creating this model, and the learning rate. So the learning rate actually tells the model at what rate does it learn from the data. So that's the information it provides. And one thing that we are also using here is we are using something called as cross-folds, basically meaning that if your data, so let's say you have one big chunk of data. The training data set is actually divided into 5 different blocks. It's divided into 5 different blocks, and each time you train, the data is trained on 4 blocks, and it's predicted on 1 more block. So basically, the idea here is cross-folds actually actually limit overfitting. So because you're training on a set of data that is not seen by the training itself, the overfitting in data actually is minimized by using cross-fold. And that's what we do by setting the end folds here.
But I thought you set up 80/20.
Yeah, so that's in addition, this is in addition to that. So the next thing that we'll do is we'll actually run the model. So this takes quite a bit of time. So you're welcome to ask any questions now, or if you want to catch up to this point. I'm really sorry. I think I should have posted the notebook earlier than this. I'll probably do that right after in case anyone is still interested in working on this. Yeah.
What's the default depth of these?
Oh, so in this case, the depth is about, we are at about 24.
Levels.
Yeah.
Can I pass a sparse matrix into GLR or into H2O?
I'm not sure about that. Maybe let's, Fabricio, do you, I think you should be able to pass a sparse matrix into GBM. I would believe so.
Sparse matrix, inside the same column, yeah. That's sparse matrix. So, are you running that on your machine?
Yeah, so it's going to take quite some time. So you can use this time for any questions or anything at all. Yeah.
How large is the data set we're using right now?
So the data set we have right now is about 700,000 records.
When you set this thing up, you set up all the features beforehand. Do you have any feature selection stuff in H2O?
When you say feature selection, you mean like create a feature? No, so H2O is only able to pick up features, so you have to define the kind of features that you want. So every data munging process that before I came to the IPython notebook, I took you through a process of how you get to a point where you've got the data ready for the H2O to load. Up till then, it's kind of outside H2O. So you'll have to define the features that you want, and then you'll have to come into H2O. That's more of domain science than machine learning itself.
What's the relationship between H2O and Apache Spark?
So we can run on Apache Spark. So we have something called a sparkling water, which runs on Spark.
But it doesn't require Spark?
No, H2O does not require Spark. We can run standalone. Yeah, there's a sparkling water talk tomorrow. So by Mikhail from H2O as well. So.
Are there other storage backends in the works? What Are there other storage backends?
No, so because we are completely in memory, the moment you get your data into H2O cluster, it really doesn't matter how you get things off. But if your output of the analysis is pretty large, I think that's when you'll have to think of how you're going to move the data out. So we can write back to HDFS, we can write back to native disk as well. So it's completely. And if you're using, like, let's say Spark, you can write the object the way you write a native Spark data frame kind of. So you can do that as well.
From your initial diagram, it looked like you had to have your data sets available across all of your nodes in the cluster. Is that correct?
No. So if you have it available to the H2O cluster, so if it's visible to the H2O cluster, we can read it in parallel. So so let's say you're talking to a Hadoop environment. Hadoop can actually read it in parallel into the cluster.
If I had just the files on my local file system, but I was using the cloud, Amazon Cloud, for example, as the H2O infrastructure.
Yeah, cluster.
I have to have my data file available to that cluster.
Yes. Yeah.
Will it read from S3?
Yeah. We can read from S3 as well. Yeah.
So while we're waiting to go over the page,
The flow. Okay. Yeah. I can do that. Yeah. So this is the H2O flow interface, which I was telling you earlier about. This is one of the most easiest ways to get started with H2O. Let's say you want to work on the same problem, using flow, and you don't have a Python API. You can, import the file from here, and you can say, so, I'm sorry? Oh, thanks. So this is how you would import the data, and then you parse it. So H2O is capable of identifying what's your field separator and things like that. Then you can set how you want each of these fields. So in our case, this would be a factor or an enumerated the priority value would actually be an enumeration. So you'll have that set as enum, and same will be with the date. And the length of the number of characters will actually be numeric. Your number of IP address will again be numeric, and number of MAC addresses will be numeric. Everything else will actually be numeric. So you'll just have to change this one field, which is actually an enumerator, and then you parse the data. It's pretty quick, and then here you actually get to the fields itself. So here you can say, how you want to split. You can say you want to split it by 75-25, or like the way we did it there, you want to split it by 80-20, and then you can run this. So now you want to train this data. So you choose the data set that you want to train, and then you'd say build a model, and here it would be a GBM. Your training frame would be, sorry, validation would be the 20%. Your training would be the 80%. Your folds would be set to 5. And in this case, your response column would be set to C6, if I'm right. Yeah. And then you can set your parameters that go into your GBM, which is 50 trees, we have set a depth and minimum number of rows. So minimum number of rows is, you want to set for the amount of training that you want to do. Like if you are okay with 2 rows having a certain value and you want to use that to train, then you can set that to 2, or if you want like 5, so you can set that out. And you can set your learning rate. You can check whether you want to score each iteration because you want to study the output of each iteration. And so then all you do is you just go ahead and say build model. So it basically does the same thing that's happening right now. But this is just a very easy interface of working with H2O. I'm sorry? Yes, we should have an airline, the standard airlines data set. We should have it on our website. Let me just pull that up. Hang on. So I'm guessing you can't see the link. Hang on, let me just pull this up. Can you see the link? Is that?
That web interface you pulled up, that was on local host, but you have that so you can run on AWS servers that you guys I have a correctly formatted data set loaded up through that, and then I assume that's some pay for that if you guys have that set up.
The
So like that interface, web interface you did, it was
yeah.
you running on your local machine. You could have the same interface that runs on AWS cluster, maybe a single server,
Yes.
and then like pay per right?
So we don't have. So it's not per unit of computation. It's just like how you would rent out, an AWS server. There must be an AMI that we actually deploy with H2O in it. So that should make it easy for you if you want to use the AMI. And
Deploy the, I have to deploy my own AWS server, right? So there's no way you don't have already deployed.
yeah, we don't have a cluster of our own that's deployed. Yeah.
Does the flow interface also provide you methods to clean data, or is it just for building the model?
No, it's basically to build the model. Yeah.
You can configure it to run somewhere other than local host. You can configure it to run somewhere other than local host.
Yes. Yeah. And that's how I'm running right now. So I'm running the H2O on my local host. Yeah. Yes.
How do you set up the mappings, like say you got a file, and
Sorry?
you want to compute up a cluster that you can H2O, is there any difference when you set up the master and slave?
So, no, not exactly. You just have to, so if you're setting it up in an enterprise environment, there is a flag where you can say, you can name your cluster, and that helps you set up your own cluster. So there could be other H2O clusters that are already there in the enterprise cluster, and they're visible on the subnet. So when you run your own cluster, the default behavior is to join to the existing cluster that's already there on the network. So if you give your cluster a separate name, it tends to form, you can have your own cluster.
So why do you use the GPM rating boost method? What does it buy you versus something else?
So yeah, so the advantage of GVM that we have right now is GVM is actually pretty robust in terms of how you do classifications in this use case, where we're taking, it's a multi-class problem that we're addressing. So this is actually helpful in identifying, in highlighting errors and identifying that more prominently. So which is why we use GVM.
Yes, please, sorry.
I have a very OCD question. When does the progress bar end?
It does very soon.
Okay, I'm just curious on
Yeah.
where on that landscape.
So the only problem right now is I've seen the screen on 1920 by 1080, so I know exactly where it ends. But this is like a 768, so I can't exactly tell you that. But it should be soon. Yeah. Oh, actually, yeah, I can probably show you another. So here too, you're actually you can see the tree number that's actually being built. So this gives you a fair idea as well as to where we are right now. I believe we are probably somewhere near the 40th.
You know what the cross validations are? You want to find the cross validations, so do you know where the cross validations are?
So
Or that's too much?
I'm not sure. Sorry, I don't want to say something wrong. Yeah.
Experience point with generalized low rank models, GLR.
Yeah. So I mean, not me, but there are other people who have actually done well with it. I usually just deal with random forests and deep learning and GBM. So yeah. Sorry, can you say that out loud?
What was the command that you did once you connected to the notebook?
Yeah, so that would be h2o.init.
When I did that, it
Can you access?
It says, the last line says connected, and that's all I read because I was.
Yeah. So the h2o.connect function is actually the new function that we have if you're connecting to a cluster. So, which is why you'll see both of it. But if you're connected, it'll actually let you know that you're connected to the server.
I'm trying to host it on a Unix server that's
Oh, okay. We're close. So actually, let that keep running. I mean, I have models from the previous iteration that I've already done. I could probably take you through that, or I should have done that earlier. So what you see here is basically the model output that we have. And this gives you all the information about the number of trees that were ran, that we used for this case, and the size of the data that we used, the minimum depth of the trees, the max depth, and the number of leaves that we use for the entire analysis. And this one that you actually see is the training part of the model. This is also the cross-validation, I mean, the confusion matrix for the training part of the validation that we see. So what we see here is that how much of error exists in how we have done in terms of classification. So you can see some of them are pretty decent, but some of them are pretty bad. I mean, I would consider this to be pretty bad. So one of the reasons some of them don't get classified really well is because of the limited data or how varied the features are across the logs. So that tends to be a problem. But otherwise, it's fairly okay. This is our training. And here you also see as to how things go across through your multiple iterations. So you see that the scoring is actually increasing. We're getting a better iteration as we go along. I mean, we're getting a better result as we go along. And this is actually our validation matrix. Let's click on this. And here you should see big errors. This one shows about 60%, wrongly classified. This is 1 of 1, which is a big problem, I believe. So, as there is limited amount of data, there's not enough data for the machine, for the algorithm to actually learn how these logs exist. So that's one of the problems that we also see. The third one that you would see is you'd see how it performs under cross-validation. Take you through that. So here too you see fair amount of breakdown in terms of errors. So here one is about 22%, and this one is about 1. So you see a fairly bit of errors. If we have enough data, things tend to be really good. Things tend to get classified really well. But some of the problems in log itself, this is kind of a real world issue with logs, is that some devices don't have so many log records compared to the other some of the machines. So this is an existing problem that we have. So that's going to be there all the time. So what we see here is that we see about close to about 99, but that's not exactly true. I mean, we all know that because some of them, because it's a multi-class problem, some of them are completely classified wrongly. So you have to take this number with probably a spoon of salt. And so yeah, it gives you how your all your cross folds actually were and how well they were. Sorry, someone had did someone have a question? Okay. Yeah. You also get scoring history. So this basically gives you a lot of information about how your model ran. You also can get your variable importance. So you see that priority ID tends to be very good at identifying these logs because priority IDs actually tell you where these logs are coming from and what they're saying. The date format is a strong identifier as well. The IP addresses are a strong identifier, but MAC addresses, which we thought could be, is not necessarily that important. The word ratios are the next set of things that are actually pretty good. So you can look at the variable importance as well, and you basically can get the same numbers out here. And if you want to look at the confusion matrix separately, you can do that as well. So the one thing that you can actually do is visualize this using your H2O flow. And let me quickly show you that. So here you see how your model is iterated and has iteratively reduced its log loss. So it's gone through multiple iterations and it's become better as you go along. And you can visualize your variable importance as well. And the same thing that we actually saw through your Python interface is visibly available here. And you can see across confusion matrix as well here. So if you want to look at the errors, it's usually on the right-hand side. So, and this comes for your training, your validation, and your cross-validation. You can also productionalize this code if you would like to. So we have a Pojo ready for that. Pojo is a plain old Java object, which is literally a Java code. All you have to do is, if you're running this standalone, compile this Java code and start running it on any server that you want. Literally, that's it. There's nothing else to it. If you want to put it, into another piece of code that you already have, like let's say you want to put it into Storm, then you literally do a call on this using the Storm library, and you're ready to go. So this part of it makes it really easy to implement an algorithm. You don't need any translation to go from your model building to productionalizing it. It's really easy to move from model building to productionizing it because you literally have to take this Pojo and deploy it. So yeah, so that's the slide. That's a presentation. Any questions up till now? Anything at all? Okay. Yeah.
I know that you guys have, so this one helps you produce the model, and then you have sparkling water to manage deployment across.
No, that's Steam. Steam. Steam.
Oh, Steam.
Yeah. So Steam is the orchestration tool.
Okay.
Sparkling water is where H2O runs on Spark.
Got it. Okay.
Yeah.
Is that, then how is this different from White Hat?
I actually am not. I do not know how White Hat does. Is White Hat an orchestration tool as well?
I just came across it.
Oh, okay. Okay.
I was wondering if that is it's an obligation or is it in addition to what you guys do? Is it some kind of utility that you can use in addition to H2O or some obligation?
Okay. I actually don't have that information. I'm sorry. So let me. If you like, I can probably email you back about this if you're interested. Thank you. Any other questions or? Okay. Thank you.